Gravitational lensing occurs when a large distribution of matter, such as a galaxy cluster, sits between Earth and a distant light source. As space is warped by massive objects, the light from the distant object bends as it travels to us and we see a distorted image of it. This effect was first predicted by Einstein's general theory of relativity. Strong gravitational lenses provide an opportunity for studying properties of distant galaxies, since Hubble can resolve details within the multiple arcs that are one of the main results of gravitational lensing. An important consequence of lensing distortion is magnification, allowing us to observe objects that would otherwise be too far away and too faint to be seen. Hubble makes use of this magnification effect to study objects beyond those normally detectable with the sensitivity of its 2.4-meter diameter primary mirror, showing us the most distant galaxies humanity has ever encountered. Unlike an optical lens, a point-like gravitational lens produces a maximum deflection of light that passes closest to its center, and a minimum deflection of light that travels furthest from its center. Consequently, a gravitational lens has no single focal point, but a focal line. If the light source, the massive lensing object, and the observer lie in a straight line, the original light source will appear as a ring around the massive lensing object, provided the lens has circular symmetry. If there is any misalignment, the observer will see an arc segment instead. Strong lensing. Where there are easily visible distortions such as the formation of Einstein rings, arcs, and multiple images. Despite being considered strong, the effect is in general relatively small, such that even a galaxy with a mass more than 100 billion times that of the Sun will produce multiple images separated by only a few arc seconds. Galaxy clusters can produce separations of several arc minutes. In both cases, the galaxies and sources are quite distant, many hundreds of megaparsecs away from our galaxy. Weak lensing. Where the distortions of background sources are much smaller and can only be detected by analyzing large numbers of sources in a statistical way to find coherent distortions of only a few percent. The lensing shows up statistically as a preferred stretching of the background objects perpendicular to the direction to the center of the lens. By measuring the shapes and orientations of large numbers of distant galaxies, their orientations can be averaged to measure the shear of the lensing field in any region. This, in turn, can be used to reconstruct the mass distribution in the area. In particular, the background distribution of dark matter can be reconstructed. Since galaxies are intrinsically elliptical and the weak gravitational lensing signal is small, a very large number of galaxies must be used in these surveys. These weak lensing surveys must carefully avoid a number of important sources of systematic error: the intrinsic shape of galaxies, the tendency of a camera's point spread function to distort the shape of a galaxy, and the tendency of atmospheric seeing to distort images must be understood and carefully accounted for. The results of these surveys are important for cosmological parameter estimation, to better understand and improve upon the lambda CDM model, and to provide a consistency check on other cosmological observations. They may also provide an important future constraint on dark energy. Microlensing. Where no distortion in shape can be seen, but the amount of light received from a background object changes in time. The lensing object may be stars in the Milky Way in one typical case, with the background source being stars in a remote galaxy, or, in another case, an even more distant quasar. In extreme cases, a star in a distant galaxy can act as a microlens and magnify another star much farther away.